Alright, so hello, welcome back. In this video we're going to, just where we're at. In the previous video we got the cube up there, we got it projected just with lines. And now I'm going to go to a plane-based approach and eliminate back faces, so faces which aren't facing towards the viewer. Now just a quick note, I was going back and forth on whether to release the completed code, and I decided to do that. So if you pop into the Vulkan Graphics sandbox repo, that completed code should be there ready for you. It's just a convenient thing. Okay, so let's get into it. Let's look at backface culling. All right, so let's start off with that cube that we had before. Let's just start with the front face. Now, before I was defining this as a bunch of edges, but let's say that we'll take it as a single plane. So I have point 0, 1, 2, and 3. And just as before, I want to define the order of points so that when my fingers curl around the edges, my thumb will be pointing towards the viewer. So here's the viewer's eye, here we're looking at the plane. Right, so I want to work out what the normal of this plane is from the points. Now, to do this, I'm going to need 3 points, and for convenience, I'll label these point A, B, and C. So then I'll subtract A from each of these points, and this will give me 2 direction vectors. So I'll have direction vector AB from A to B, and then I'll have a direction vector AC, and well, AB is a tangent, and AC is also a tangent because the direction from A to C is still completely inside the plane. So the word for every plane has 2 tangents, by the way. One of them we call the tangent, the other one we call the bitangent, but there's no particular reason for the naming convention. We could reverse, it would be the same thing. But the big concept is if we take the cross product of AB and AC, then that produces the normal vector. So just imagine this is coming out of the plane, so it's orthogonal to both of those vectors. And the convention here is because we're going AB cross AC, imagine curling your fingers from AB towards AC, the direction of your thumb is where that normal is going to point. So then we want to say, okay, well, how does this interact with the viewer? Now, in our traditional coordinate system, we had it so that positive z was towards the viewer. So we would look at the z component of the normal and say, well, if the z component of the normal is positive, it's visible. If it's negative, it's non-visible, invisible. But in this video, I'm going to hit these points with the projection transform first, and then do this check. And when we hit it with the projection transform, the z direction actually reverses. So it's a little gimmicky, but we'll fix it up in a later video when we check this in world space. But anyway, that's the idea. Of course, in addition to this, we have a bunch of other planes, and it's important to set these up so that they are always going the right way. So for instance, if I look at the back plane, I want to put these in the reverse order so that when my fingers curl around, my thumb is going back. That's what it should be doing. And then on the top plane, if I put my thumb up, fingers around, I find that I actually want to, this edge has to be defined in the opposite order. Same with this edge when we look at the top plane. So anyway, let's jump into the code and see how this all boils out, how this comes out. All right, so here we are in Visual Studio at the project. Again, if you haven't been following along, link down below, Vulkan Graphics Sandbox. Now let's open up in the control folder our app header, and previously we did the lines test and the projection test. Now let's make a backface test. Okay, and we'll just open up the source file, go to the run function, and see here we can just comment out projection test, and I'm saying now when I run this I want to run the backface test. Now there's one more thing I'm going to add, and that is I don't want to just look at the cube, I want it to spin around, I want to have some things going on. So let's go to the header and declare that we'll have a float called theta, give it a start value, and we'll be updating theta every frame. So now we'll just close all of this down, go to the projection test, copy all of this, and paste it, and I'll just go through this. So we'll have 8 points. We've defined the 8 points here. I'm actually pretty happy with that. And now instead of having edges, we'll have planes. So we'll have 6 planes, and I'm going to call this the plane vertices. There we go. So the first, I'm actually going to modify this a little bit. So I'm going to have a 2-dimensional array that is each set of plane vertices will be a set of 4 integers. So I'll just put this one in here, and now this isn't going to be a lot of fun, so I'll just quickly fill this stuff in. Okay, there we have it. Now, let me just investigate. So this is from my previously completed notes, but let's have a look at this. We have 0, 1, 2, 3. Now, if I look at the points 0, 1, 2, 3, what they have in common is the depth is always at the closer value. So I'll call this my front face. 1054. Okay, so 1054. We have a positive y, so I'll call this my top face. 3650 has a positive x, so I'll just go right, and I'll just complete the rest of these. Something like that. Okay, so if we were to dig in and debug this more closely, it's really good to see which face is which in our plane, in our cube. Okay, so let's not log this out. It's fine, there's nothing wrong with it, but I think we're happy with that. Let's increment our angle. So we'll say increment theta by a little bit, but in order to make this frame rate independent, I will multiply it by the app's frame time, that is the number of milliseconds that it took to render a frame. I'll take that as a proportion over 16.6, which would correspond to 60 frames per second. So if this is going faster, it will slow the angle increment down to accommodate for that. And I'll also do a little mod check. So I'll say if theta, I said theta, is bigger than 360, decrease it. Okay, so that's all well and good. Now what I want to do is I want to start spinning the cube around. So I'll say make a 4D matrix called model, and I'll make a Z rotation. And now what I'm going to do is I'm going to stack on a whole bunch of these. So if I rotate these points right now around the z-axis, their separation from the z-axis is a bit weird. The cube, if this is our axis of rotation, instead of being centered around the axis to spin, it's going to be out here and it'll be spinning and coming behind us, and that's really bad. We haven't covered that yet. So what I'll do is I'll just center this around the origin. Okay, so we can now spin it around the axis, and then after we spin it, we'll send it out in front of us. So what I'll do is I'll multiply a matrix 4 with a matrix 4. For my original matrix, I'll take the model matrix that I just produced, and for the second matrix that I want to stack onto that, I will make one. So I'll go make a translation, and then the translation amount, I'll make a vec3 of, let's go -5. We'll make it nice and out in front of us. So I've got the model transform, and then I've got the projection, and what I want to do is do both of those in one. So I'll make a new mat4, which I'll call final transform, and what I'll do is I'll multiply. For the original, I'll take the model transform, and then I'll stack onto that the projection transform. So now, I'll just multiply that on, and then I'm still going to have issues because I just need to fix up the rest of the drawing code. So let's get rid of this logging stuff. We'll still put things in screen coordinates. That is good. Okay, but now what I'm going to do is I'm going to do this for each of the planes. And now I'll loop through again. All right, so this is getting a little fiddly. I should start talking through it. So I'm accessing into the transformed vertices, and the index in there is the ith plane looking at the jth vertex there, if that makes sense. So again, if we look back up here, the ith plane would be, this plane, this plane, this plane, and then the jth vertex would be each of these bits within that. So I've got that. Now what I'll do is I'll take the data, the 0th component, and that is my x, and then I'll do this again to get the y. That would be the one component of the data. And then for the next point, well, what I want to do is I want to plot between this point and this point, and then I want to plot between point 1 and point 2, and then between point 2 and point 3, and then from point 3 looping back around to point 0. So for point B in each of these, I'm going to take add 1 to the component, but then take its modulus under 4. There we go. So now I can pop back here and say, okay, I'm drawing from XA There we go. Okay, so let's give that a go and check that we are in fact seeing a plane. Oh, okay, what have we got? Whoops, I've not renamed it actually. Okay, let's give that a go. Okay, excellent. So as you can see, we are rotating around the z-axis. It's not very exciting, but it's correct. Okay, so let's stack on some more transformations. Let's go take this, and we'll now put on a rotation around the x-axis. Yeah, and just double the rotational speed. Okay, something is looking a little off about this. Let me just check that again. Yeah, right. Something is definitely not. That one looks okay. Something's definitely up with this. Well, now it looks okay. I don't know. That looked weird, right? Let me try that again. Let me know in the comments down below. Oh. No, now it looks okay. Okay, look, I'm really not sure. Maybe I'm seeing things, but those first few iterations looked weird, right? Anyway, so here's what I've done. We've got an Z rotation, followed by an X rotation, and then a Y rotation, all at different angular frequencies. Okay, so we apply that rotation, then we send the points back in front of us so we can see them, and then we project them. Okay, so we are almost done. But as you can see, right now every single plane is being drawn, even though some of them are clearly behind the camera. If we look back here, these back faces probably shouldn't be drawn. So for each plane, let's calculate the front face and the back face. Sorry, the tangent and the bitangent. Get the normal and check this. So first of all, I'll just get 3 points. Okay, so I'm just reading off the first 3 points. So I'll go A, B, C, 1, 2, 3, 0, 1, 2. Okay, so again, I'm literally just accessing for each face the first 3 points. Okay. Okay, then I take the vector subtraction, so the component-wise subtraction. And by default, under the hood, I'm storing vec3s actually as vec4s because I have that much space available anyway in a 128-bit variable. So I just set the fourth component as 0. It actually doesn't matter at all. So to get the bitangent, I just take the direction from A to C. And then I will take the normal by performing the cross product of the tangent with the bitangent. Okay, so finally the test is the z component of the normal. So I'll say, alrighty, if the z component of the normal, now really what this should be, if we were doing it properly, is it should be a negative number because the viewer is at a positive z and in world space it's pointing back. Positive Z should be the 1. So if this isn't working, then we'll continue and just go to the next plane and skip all of this drawing. So let's give that a go. And it's not working. And the issue here is that once we hit the points with the projection matrix, that puts them in view space, not world space. And in view space, the convention is flipped around. So right now, we'll go back and we'll fix this in a later video, but for now, and we'll actually build on this backface culling in a later video with other things. But for now, we'll just reverse that condition. And there we have it. Now we are eliminating the back faces correctly. Yeah, starting to look very cool, starting to look satisfying. And there we have it. So, very nice. We are eliminating back faces. It's nice. It's looking good. So thanks for checking this out, and I'll see you again in the next video where we will, well, handle what happens basically when that cube goes off the screen. All right, have a good one. Bye.